Okay, section 4.5, we're learning about quadratic inequalities. If you recall from previous math classes, inequalities means that it doesn't have to just be equal, it could also be greater than or less than. So far we've been learning about quadratics, where y equals some numbers that are related by this equation. And the graph shows us all the points that work for that situation, the points that are along this parabolic shape on a graph, because that is where y is equal to those points. However, if we want to use some inequalities, we could start thinking about it being greater than that graph, in which case, if it's greater than but not equal to, it wouldn't include the graph itself. So to show that, we would do a dotted line, and then shade the area above the graph to indicate that it's the points that are greater. Okay? Or if y was less than or equal to a quadratic, it would be the area under the quadratic. And this time, because of the equal sign, it would be a solid line and then be shaded underneath. Okay, so that's a little bit of a review from quadratic inequalities that you might have done in Algebra 2. That's if we're dealing with y, and so we're looking at the graph where those values, where the y values are greater than that graph, or the y values are less than that graph, okay? But instead of y, we're actually going to be dealing with just x values and greater than or less than a number, a numerical value. Usually we want that number to be 0 because it makes it easier to work with. And we're solving the inequalities, okay? So the part I just did was just kind of some review of graphing quadratic inequalities, but now we're going to do solving quadratic. Sorry, I spelled it wrong. I have to sound it out to spell it right. Quadratic inequalities. Okay? So for example, instead of y, if I have that ax squared plus bx plus c is equal to 0, then that would be where the y value equals 0 on that graph. So we might have our entire parabola that fits the graph, but all that makes this true, the only thing that makes this true, is the X-intercepts. So the solutions are just the X-intercepts. Okay? Well, what if we switch that a bit so that instead of just equal to 0, and I prefer having my number over here instead, so like ax squared plus bx plus c equals 0. That's easier for me to understand what's happening. Okay? So this stuff was formerly what we were saying is equal to y. Now we're saying it's equal to 0 instead. Okay? So if we look at something like this, where it's greater than 0, then that would be the part of the graph that is greater than 0. So above the x-axis, because this is where y equals 0. So these right here are where y is greater than 0, because it's above the graph. Okay? But unfortunately, the graph itself is not our solution. The graph can just help us find the solution. The solution is the x values that this graph shows. So the x values from like negative infinity to wherever this point is, and then from this point to positive infinity, and that would be the solutions to this inequality. We just use the graph to help us find those solutions. Okay, let's look at a couple of examples. We are going to solve x squared minus x minus 12 greater than or equal to 0. So what that means when we're solving is we're trying to find all the x values, that make the inequality true. We're going to do that in this section by using a graph. Okay? The first step is to find the x-intercepts. Why the x-intercepts? Well, that is where y equals 0. So those are the points where if we go above, it's greater than, and if we go below, it's less than. So those are those critical points where it changes from greater than to equal to less than. Okay? So we're going to find those x-intercepts by factoring, or if it doesn't factor, we will use the quadratic formula. Okay, so we look at our original problem, which does factor. So we have an x times an x, and then factors of 12 that will add up to, well, factors of negative 12 that add up to negative 1. So it's negative 4 and positive 3. And then you can FOIL it to check your work. That means that x would equal 4 and x would equal negative 3 if we just wanted to find where x equals 0, or where the answer is equal to 0. Okay? Now what we do is we graph those points. So 1, 2, 3, there's a point at negative 3. And 1, 2, 3, 4, there's a point at 4. Graph those points, and then we don't even need the vertex of the parabola. If you really wanted to find the vertex, you could find it, but all you need to realize is that this parabola is pointing upward. It opens upward, and so therefore our answers greater than 0 are going to be the x values included in this portion of the graph and the x values included in that portion of the graph. So the way that we give that answer, we could do a set notation, but instead we're going to do interval notation. So the solutions for x would be negative infinity down to where this is equal, because notice how it's equal to 0, so it includes that point. So down to negative 3, including negative 3, because it's okay if it's equal to 0. And then from 4 to positive infinity. And that is our answer. Let's do another example. Negative 2x squared is greater than negative 11x plus 15. First of all, we want 0 on the right side, so let's move everything over so we have 0 on the right. So negative 2x squared plus 11x minus 15 is greater than 0. Okay, let's go ahead and factor this. This one's kind of some ugly factoring here. So negative 2 times negative 15, we'll just do it off to the side. Negative 2 times negative 15 is a positive 30. So we need to think of all factors of positive 30 that might add up to 11. So there's 5 and 6. Oh, there it is. There's 15 and 2. There's 10 and 3. 30 and 1. So obviously the factors that add up to 0 are 5 and 6. So now we do the separating this term into two terms. 5x plus 6x minus 15. I think I've done something wrong. No, I haven't. It's fine. Nope, it's fine. Okay. Now we factor by grouping. All we can take out of this particular factor, well, I don't like having that negative in the parentheses, so I could take out a negative. In fact, I'm just going to take out a negative x. So left hand side, if I take out a negative and an x, is I have a 2x. But be very careful because I'm taking out that negative. That turns this positive 5 into a negative 5. Then here I can factor out a 3, which leaves me with 2x, minus 5. Oh, and it matches, just like it should. So now we can take this factor out of the whole thing. So 2x minus 5 and negative x plus 3. Now we take each of those individual factors equal to 0 to find our critical values, or our x-intercepts where x actually equals 0. So 2x equals 5, or x equals 5 over 2. And then negative x equals negative 3, so x will equal 3. Okay, then for our graph to help us, we will put 5 halves is 2.5, so there's a point there. And 3, oh my goodness, right next to each other. Now this particular graph, because of the negative, opens downward. So our parabola, and again we don't care where the vertex is, we just care where the intercepts are and that it's pointing downward. Again, this one is greater than, so that means above. If it had been less than, it would be below. And it's also not equal to. Notice how there's no equal sign, so it's not going to include those numbers. So it's above, but this time, because the parabola is going upside down, it's going to be this piece in between those 2 points instead of a point from negative infinity and then a point to positive infinity. Okay? So our answer on this problem will simply be between these 2 points. One of the points is at 2.5, or 5 halves, and the other point is at 3. So it's a very small interval of solutions from 2.5 to 3, where x satisfies this inequality. And of course, notice how I put parentheses instead of brackets, because it's not equal to on the graph. So technically those should have been open circles, but that's not a big deal, because the graph is just to help us get the answer, and I've got my answer right.